Our last video, we discussed about the unique solution, infinite solution, and how a system of equation has no solution, and also discussed about the geometric interpretation of a system of linear equations, and ultimately end up with two very important questions. One, as we are unable to draw a picture of a four or more variable linear equations, then how can we conclude that the system has unique solution or infinitely many solutions, or the system doesn't have any solution? Okay, that's mean what is the algebraic interpretation of finding the fact that the system has unique solution or infinitely many solutions or no solutions. And the second question was that as we are dealing with four variables, four dimension or more, then is the geometry in 2D, 3D, the properties of geometries, the distance, the angle, how can we define these properties in four dimensional, 4D or more dimensions? Okay, so we will definitely answer these questions, discuss these questions, but these are very much higher level of linear algebra. So first of all, we need to understand the basics. So in this video, I will go through lot of developments. Okay, and so let's try to understand the developments step by step. So first of all, I will start from I would say a very important. In Chinese mathematicians, we already discussed that how they wrote these equations cleverly. So as to solve the equation, we know from our very childhood that we don't how we solve this system of equations, but the thing is that we don't need the actual coefficients to ultimately the operations what we are doing. We don't need the actual coefficients, so we can ignore the coefficients. Sorry, the variables. So I can ignore the variables. I no need the variables. The only thing I need is the coefficients. Okay, so mathematicians noticed this particular thing, and they ultimately tried, and ultimately Chinese mathematicians, they wrote these things like I already show you that just in the box like this, but they never gave a name to this. They just wrote it like this, and they told that this is a method of solving the system of equations. Okay, now time passed, and ultimately when mathematicians were solving this rectangular box is not arbitrary actually. Okay, what is arbitrary actually? That's the coefficients actually. The each row actually one representing an equation. Just we can put the x, y, z here. The each row actually representing an equation, and one equation. Each column actually representing one variable x, y, and one variable that's an x. This is y. This is z. Okay. The grid preserves which number belongs to which equation and the variable simultaneously. Okay, in China, there was a counting board also. I mean, where they just they keep the numbers and just do the multiplication. Okay, so those time. Okay, and this is very much interesting thing to understand. Actually, how the concept of matrix is evolving. I think you guys are able to understand how the concept of matrix is slowly developing. That yeah, we no need the variables. We just need the coefficients. Okay, and this is actually representing an equation, a row, an equation, and column actually representing a single variable. These are the things where actually very much important to understand for the concept of matrix. Okay, now so the development of matrix happened, we can see that not just a mathematical object. This is actually first happened just to use the math to write the as a symbol, I can say. Okay, but now mathematicians gradually realize that, let's say if I add two grids, okay, like two boxes, if we want to multiply it, what will be the result? Okay, so this thing actually, this particular thing did Arthur Kelly. Okay, so in ancient China, mathematicians, okay, especially ninth chapter of mathematics in the book, okay, they arrange the systems like this. Okay, we already go through these things. Okay, now actually Leibniz and Kramer, okay, study the determinants, okay, for the matrix, but they told that matrix means the mother. Okay, that's they actually not used the used matrix as operation. They just used it as a tool. They told that the determinants are coming from matrix. Okay, now ultimately the birth of matrix happened actually by, you can say, the Arthur Kelly in 1858. Okay, so he published the books, famous paper, Memories on the Theory of Matrices. In his paper, he actually defined the matrix addition, the matrix multiplication, okay, and other things. Now our objective is to how actually he defined. To understand this is actually very much interesting thing. to understand the evolution of matrices. Actually, the understand if you understand the how the matrix addition is defined, how the matrix multiplication is defined, you will understand a lot of things inside linear algebra. Okay, so we will try to understand how actually the addition of matrix is defined, how the multiplication of matrix is defined. Actually, how the multiplication of matrix, everybody we know the what is the multiplication of matrix. Why is the multiplication of matrix is like very much abstract way. I mean, just we take a like, I mean, very much messy way. Okay, so we will try to decode it in this video. Okay, so let me take an example. Okay, and I will slowly go through in deeper sense. But before that, I already discussed with you that geometry was developing, okay, in this time. Geometry actually gave us the answer of the how the multiplication of two boxes, I mean the matrices, okay, can be defined. Before that, let us start with the addition. Okay, so as we already discussed you that actually adding means, okay, let's say, let me take two system of equations. Okay, let me write it, this two. Okay, now if we want to add them, okay, so what you do, just if you want to add them, okay, then add it with it. That's mean just add this first equation of the this system with the first equation of this system. Okay, so this will be 6x plus 2 plus 3 5y equal to 7. Okay, and 3x plus x, that's mean 4x plus the 4y plus y, that's mean 5y equal to 2. Okay, that's mean just, I mean, if we want to add these two systems, we do this kind of things. Okay, so this is very much obvious, okay, to understand the addition. So if we write this system as the matrix from 1 2 3 4, just the coefficients. Okay, so the addition of these two boxes will be defined just at the coefficient 6, okay, 5, 4 and 5. Okay, so this is the addition. Okay, this is very much obvious, I think. Okay, now the multiplication. But before that, let me tell you one thing. Like defining something, what does it actually mean? Actually, what Arthur Cayley did already, I mean, how the concept of these kind of boxes came, and Arthur Cayley actually understand the significance of these boxes. That's mean the matrices. Okay, so I am calling this as matrices. Okay, so he, as the boxes have significance, so definitely we need to define some operations, because if we have, let's say, all 2 cross 2 boxes, okay, that's mean if all 2 cross 2 boxes, if all 2 cross 2 boxes are there, okay, that's, so we need to define something, because if we have only the boxes, we don't, I mean, we have no, I mean, need them. So we need something operations on them, so that these things are actually defined. So addition, we can define the addition like this also: 1 plus 3 4, 2 plus 5 7. But we don't define the addition like this. We define the addition 1 plus 5 equal to 6, 2 plus 3 equal to 5. Why we define this? Because if we define the addition like this, okay, that means the ultimate result will be closer. Closer means this will obey some this will obey some significance. Okay, this has some significance, and geometrically, if you try to understand this, you can able to understand these two system of equations actually representing two pair of lines. Okay, so ultimately adding them, okay, ultimately we end up with another line. Okay, so which we can also box with box, I mean, we can also write them as matrix form. Okay, but yeah, if somebody can say that if I add these two coefficients x with 3y, okay, is it not a line? No, this is how this is a line, because if we add this one with this, okay, this is not a line anymore, because you can see that's mean x plus 3y 2y plus 5x, these kind of things will happen. So this is not a line anymore. Again, one thing is possible is that, let's say, for this x I add this x, okay, and this one, I mean, one with this, okay, and this one, and this is actually very much messy. If we have something simpler form which is definable, so why will not define this? This is the most simplest thing, we can define it, and this is closer, and this is ultimately giving us a system of lines again, pair of lines again, which I can write is the matrix form. So that's why Arthur Cayley took this operation, okay, not other operations. Now multiplication. This is very much important thing. Multiplication. I already told you that geometry, after the Chinese mathematician discovered the how to solve the linear equations. Okay, the geometry started developing. Okay, and Rene Descartes actually gave us a lot of ideas of geometry. Okay, and the geometry ultimately show us the path how we can define the multiplication of two matrices. Let me take an example. Let us try to understand, because again we have to define the multiplication as if the this is obey some, okay, obey some meaning. Okay, we have to define the multiplication like this. This is ultimately obey some meaning. So Arthur Kelly did this. How can we define the multiplication? We define the addition. How can we define the multiplication? Let me explain it with an example. So let me write the example. This one, let's say somebody wants to rotate the frame of reference. Okay, so how can he write these things? In geometry these things are exist already. Okay, so Calais noticed these things. Okay, that we can actually rotate. The rotation is here. That's mean we can write the rotation. We already know these things in geometry, so I am not explaining why these things are happening. Okay, so we can write this as, this is the rotation form. We know this thing. That's means ultimately this and this coordinate system is like this. So now Arthur Calais actually noticed one very much interesting thing is that this thing, we can write this thing as transformation. Okay, how we can write this? This is a notice that this is a 2 plus 2 transformation. These things exist in mathematics. Okay, and Arthur Calais just noticed that this can be written as transformation. Like how this is a 2 plus 2 transformation. Arthur Calais noticed this thing. How this is R to R. Okay, and ultimately we can write this thing as this. Okay, the xy, any xy point, where the where the transformation xy point is going in under this transformation, nothing but here x cos theta plus y sin theta, comma, minus x sin theta plus y cos theta in this point. Okay, now this is great breakthrough. Okay, writing the equation like this. And let me take one more transformation. Okay, this reflection, in this case, if there is a point x comma y, sorry, if the, okay, in the rotation case, okay, if xy is a point, let's say this one is xy point. Okay, and after the theta angle rotation, this is ultimately going, or let's say this one is x comma y point. Ultimately after a theta rotation, this is going, okay, theta, this is going theta angle and ultimately going here, let's say. Okay, this is x dash y dash. Okay, this is the rotation. Okay, now the reflection, if this is x comma y point, ultimately after, let's say this is reflection. This means reflection means if this is a mirror, x-axis is working like a mirror, this is just going here. That's mean the x position is remains still and just the y is just changing. That's mean if I write this as x dash y dash, what will be the x dash? X dash actually remain x, and what is y dash? That means 0y, and y dash equal to 0x minus y. This is actually happening. Okay, this can be written as the transformation from R2 to R2. I think you guys also can write this very much easily. Okay, t x comma y ultimately going here and here. I can write this as x, this is as minus y, so I am not writing these terms. Okay, so this is ultimately going there. Okay, that means these two things actually can be written as transformation. Now Arthur Calais noticed one thing, that if we just compose these two transformations, let's say this is t1 and this is t2 for our convenient. Okay, so if we compose these two operations, okay, that's mean, let's say if I first I t2, then I compose t1, and if I do this thing, that's mean t2, if I first apply t1, that's mean this is x cos theta plus y sin theta, and then minus x sin theta plus y cos theta. Okay, after I applied t1 first, then after applying the t2, what will be this? Just this one will be remain same, first term x cos theta plus y sin theta, and they are just minus sign will go, and we will end up with this. So Arthur, one thing is noticeable is that two transformations Okay, and these two transformations, if we compose them, this is ultimately ending up with another transformation. Okay. So what is this doing actually? First of all, we are applying T1. That's in first of all we rotating. That's mean if I draw the picture, first of all we are applying. Let's say this is x comma y point. Okay. First of all we are applying. These are all geometry. Okay. I think you guys are know about these things. Okay. I'm nothing. I'm not telling any linear algebra here. Okay. I think everybody should know these things. Okay. In their lower classes. So if this is a point, if just I apply first T1, that's mean I am applying the rotation first. Okay, that's mean the xy plane is rotating theta angle. Let's say this is the theta angle rotating here. Ultimately the xy plane is xy is the point xy is coming here. Let's say this is x dash y dash. And after that T2, that's mean the reflection with the x-axis. So after the reflection that will be this. Okay, this is let's say x double dash y double dash, and this x double dash y double dash is this one. X double dash equal to this, x y double dash equal to this. This is the thing. Okay. Arthur Kelly noticed that this rotation and reflection is a transformation, and this transformation, after composing these two transformations, we are ending up another transformation. And one thing actually we are doing for many times before is that we are just writing these things at matrix form because we are interested with the coefficients. Okay, so we can write the coefficients in matrix form: cos theta, okay, sin theta, and this is minus sin theta, this is cos theta. Okay, and in this case again we can write that 1, this is 0, this is 0, this is minus 1. Okay, Arthur Cayley noticed that ultimately these are the two matrices. If I take, let's say this is A and this is B. Okay, this is B. Now Arthur Cayley noticed that ultimately if I define the multiplication, I mean ultimately these two transformation again giving us a transformation. That's means this is close and this is the most closer and this is the most basic thing. Okay, for defining an operation, for defining. So he that these boxes, these boxes are, I mean first of all these boxes we define the addition. Okay, and if we able to give the thing, give this the multiplication like this, the composition, let's say AB, that's mean I am telling that okay, AB, we compose it like this. Let's say BA means first of all, because in this case we first use the T2, that's mean here you also use the first B1 B, so BA, that's mean we just doing 1 0 0 minus 1. Okay, and A is this cos theta sin theta minus sin theta and cos theta. Okay, so this one. So ultimately if we define the multiplication of two boxes like the composition, okay, ultimately we end up with this, no, with this composition. So he told that if I define this like this, let's say this one is actually nothing but, let's say, cos theta. Okay, now the sin theta, and this one is sin theta minus cos theta. Okay, like this. So if we define the multiplication like this, okay, so this is obvious and very interesting actually result. And ultimately this is the matrix multiplication. If you do the matrix multiplication, this will be the result. Actually this will be the result. We just wrote this. This is the matrix multiplication. 1 0. I think everybody know in 12 standard that what is the matrix multiplication. 1 and this is 0 cos theta. 1 into sin theta plus 0 into cos theta, that means sin theta. 0 into cos theta minus 1 into minus sin theta, that means sin theta. And 0 into sin theta minus 1 into cos theta minus cos theta. Ultimately you see that cos x, okay, ultimately we end up with cos x plus y sin cos x cos theta plus y sin theta. Okay, x sin theta minus y cos theta. Okay, this is the ultimate result. Okay, so this is the thing. Actually we are if we are multiplying two matrices, what we actually doing, we are multiplying two transformations. Okay, so again if I write one more, let me take one more example. Let's say this one, if these are the two transformations, okay, or these are the two, you know, these are two line segments if you say. Okay, so this is our actually two transformations. We are actually using them as two transformations. Okay, and last we are doing is multiplying them. Okay, these are actually two transformations, and we are multiplying it. Okay, multiplying, these are actually two that means these two matrices are two transformations, nothing but two transformations, and we are composing two transformations, and actually the composing result is the matrix multiplication. Okay, what is the transformation? So transformation is like this: t1 r2 to r2. Okay, and t1 x comma y is equal to, okay, 2x plus 3y, 5x plus y. Okay, so we can't write this as 1 or 2 because this is a particular result. Okay, we are taking particular lines we are taking. Okay, and t2 is equal to, let's say, because I can put any value of xy. Okay, here, so these are the not 1 or 2. This is a linear solution. So better we write is at x dash y dash, or this is x double dash or y double dash, because we can put all the points of r and y. And this is I am writing, that's mean 1 or 2 I am particularly writing, that's mean I am telling about a particular line segment. And if I am writing this is I am not telling about a particular line segment, this is actually a transformation. So okay, and what is this actually? X plus y comma 2x plus 5y. Okay, just I am doing the transformation t2 compose t1 x comma y. Okay, so if you go through all the thing, okay, you will ultimately end up with the multiplication. Okay, so I am writing all those things. I am not writing all the things. If I think you guys can check this. Okay, and will be definitely understand what is actually happening. So one question that can comes to your mind, that why I vanish the two constants. So let me tell you, we don't actually 2x plus 3y. 2x plus 3y, what is the line? Let's say this one is a line, 2x plus 3y. So if I put something, let's say 1 here, okay, so this is a particular line segment. But if I am putting x dash here, so this is not a particular line, this is just I mean, if I change the value of x dash, then the line will go up or downwards direction. Okay, so the problem if I take 1 is this is not a transformation, because line segment is not a transformation. We cannot write this like this. So matrix multiplication can be defined like this. Okay, and transformation, that's mean, okay, and these are not a transformation. Okay, so we cannot actually we are actually doing this thing, we are actually not treating them as the matrices. If I am taking 1 or 2 or 2 or minus 1 here, okay, we are not actually dealing with the transformation. But if I put x dash y dash x double dash y double dash, that's mean this is a transformation. Okay, this is all about the matrix multiplication. And I think I able to tell you how the matrix multiplication is defined. Okay, and actually, what if I take all the things in brief, all the 3 videos in brief? First of all, Chinese mathematicians first developed the system of equations and how to solve them. Okay, and they wrote them in a box. Okay, but they never gave them name. Now Arthur Cayley, and before Arthur Cayley, a lot of mathematicians used these system of equations. I mean, they used them as boxes, but never. I mean, and Leibniz actually used the determinant form. He don't define any relations, any operations of matrices, but he told about the determinant. Now after in Cayley, 1858, Cayley actually ultimately defined the addition and multiplication of matrices. And why the defining of addition and multiplication is important? Because if there is a lot of set of numbers, and if I want to find the relationship between them, then we need some any operation. Okay, so that the values of the set is, I mean, the related each other or not. If I give you any random set, okay, 1 2 3 4 5, okay, so this has no significance for me until this has any operation, this has any relationship. I mean, the values in the set has no, if the values in a set is no relationship between them, then what is the advantage of having these elements? So first of all, find the relationships any. So these relationship actually you can understand as the operation. the addition, the multiplication, and after defining the addition and multiplication, the importance, the significance of matrix actually, the significance of matrix uh, actually enormously increased. Okay, and ultimately, and geometry, how the geometry arrived. Okay, and how is and we understand that what is the relationship of the matrices with geometry, and how the transformation actually, the composition of transformation is actually implying the multiplication. Okay, and actually how we are writing the transformation as matrix form, this is also understanding, this also very much important. Okay, I think this is everything for today's video. Thank you.